By the way, this is as good an understanding of probability as the one which says that you should all take a bomb with you when you go on the flight next time. You know why? Because the probability that there are 2 bombs on the plane is infinitely low. So if you already have a bomb with you, then there won't be any other bomb. And you're a good guy, you're not going to use it. So everybody would be safe. And if you do it, of course, if you believe this argument and do it, you deserve what you get. But these are all fallacies of probability, fallacies of independent events. But the old woman actually didn't understand the probability, that's why they were doing it. But anyway, the bigger issue is, unbeknownst to you, each of these might have slightly differing probabilities of reward. And what you do in essence is you're trying to figure out the model of the reward, what is their probabilistic reward, how many times do you have to pull it such that you will get. On the average, if you do it infinitely often, what's the expected value of the turn from here, here, here? And if you can figure that out, then if one of them has a higher expected value, you try to pull that more often. So to be a good gambler, you essentially don't just go and give their money away right away. You want to give the money away slowly to the gambling establishment. You spend some time, quote unquote, exploring the machines. And then you get the system. The system is this, you're figuring out the model. And then you exploit it. And so in fact, exploitation trade-offs, the classic problem people think of is the bandit problem. So if you keep hearing things like multi-armed bandit problem, the one-armed bandit problem, you know what we're talking about. Okay. Finally, so we basically talked already about one way of doing it. The simplest is this random actions. Every time flip a coin with a probability epsilon, act randomly, probability 1 minus epsilon, act according to the current policy. This is where we started from. This is like the 0th idea you should be able to do. Okay? Now, of course, random actions have problems because the higher the epsilon is, the longer it will take for you to converge. But if, on the other hand, if you make epsilon to be 0, then you will never converge. You will converge to something, but not the optimum. Okay, so what you can do, other ideas that you can do is, as somebody was saying, keep track of the number of times a state action pair has been explored. And if you have done that often enough, then don't explore it again. Do you see what I'm saying? Okay, so this essentially doesn't do across the board random. It says, I prefer new experiences until I've been shown that those new experiences are basically useless. Okay, and the way to do that, this is a cute way. Instead of, so the cute way is basically this. You define a pseudo value function for the states. The pseudo value function for the states is the current value of the state plus k by n. The k is a novelty reward. And n is the number of times you have come to this state. If it's the first time you came to this state, you get a very good novelty reward. If it's the 15th time, k by n becomes smaller and smaller. If you are done infinitely often, k by n becomes 0. So in fact, asymptotically, this pseudo value function is the same as the true value function. Do people see what I'm saying? Now, if you use this as the value function to do your policy, then in essence, you have built into your policy this look for the new states. Okay? So that's a much better idea. And in fact, this is a better idea of exploitation than just all the time doing random or doing random with a fixed percentage. So this is a an idea that you want to basically keep in mind. So the important thing is that you are essentially giving a novelty reward, and the novelty reward wears off as you keep going to that place many times. Again, notice the solution is very simple. As I said, in reinforcement learning, the problems are phenomenally deep. The solutions are simple. And showing that the solutions actually converge is again interesting, that being an undergrad class, I'm skipping those details. Okay, the only thing I actually shown was, I showed you, for example, that this won't converge. Okay, but I didn't show you specifically in any proof, in any formal proof, that either random policies or random policies which do this more interesting novelty reward will converge. Kind of intuitively understand they will, but if you are actually into the mathematical background, you have to show those proofs. Okay. Okay, next we look at, that has taken care of active learning, model-based learning, both passive and active. Then I'm going to look at model-free learning. Okay, remember that's what I said last time, that there is model-based active, model-based passive, model-based active, model-free passive, model-free active, and in between we talk also about exploration exploitation. Exploration exploitation is important anytime you do active. That means you are not given a single policy. And you are trying to do the optimal policy while behaving in the world. Okay. So it turns out that, so the big issue in model free is you would not learn T and R. We don't need T and R at all. Instead, we just directly learn pi. Okay? In fact, to learn pi, you actually basically learn B and you convert B to pi. Okay? So, the first example that you already know, which did not compute T and R and computed B directly, was the very first idea we tried, which is this Monte Carlo simulation. Where if I give you a single policy, which is the passive case, then that's basically, I simulate the policy many times. That means I execute the policy. This idea of executing the policy is also called unrolling the policy. Okay, you basically follow the policy for a certain amount of time, and then you use that to figure out what the values accumulated are when you started from 1, and you take certain amount of following of the policy. And then you average that to get the true value that you can get from that particular state. You remember this, right? This was last class we discussed. The thing is, we started from there and said, we went from there to let's learn T and R. Okay? But this by itself is not learning T and R, it's learning B directly. By the way, sometimes instead of writing B, I'm writing U, but I hope that's not confusing. Okay? That's model free, because we are not computing transition and load. But this is a useless algorithm in the beginning. We started this and said this is kind of inefficient because it does not take into account the fact that the values of neighboring states are correlated. Remember? That's why we then went to T and R, and then we used Bellman update, Bellman equations to make sure that you actually take into account the correlations between the neighboring states' values. Okay, so now problem is, if I'm going from here to make this more efficient, but I want to do it still model-free way. I don't want to learn T and R. What can I do? It turns out that's where essentially there is this idea called temporal difference learning. Once again, it's one of these things that looks like too good to be true. How come it's so simple to do this? And you kind of need to understand why it is actually working. So, the big idea is, why even bother learning the transition model? Okay? If you essentially just keep acting in the world, the transition model, the true transition model is actually guiding you. So you would go to the neighbors that are more likely to occur more often. Did you guys understand what I just said? If you wound up doing an action A from state S, and if state S dash is supposed to come with probability 0.8, then if you do that action in that state 10,000 times, then 8,000 times, close to 8,000 times, you're likely to experience S dash. And only the rest of the times you're experiencing some other state. So you can actually use the world as its own model. You see what I'm saying? So that's basically, and the point is, if every time you see a neighbor, remember the, oh, this every time, can people still hear me? Okay. Every time you see a neighbor, what you basically are going to do is, remember the whole point of the previous idea is it doesn't realize that neighbors have correlated values. That was the problem, because it was this, after computing the value of this state, it starts computing the value of this state freshly, as if they had no connection. I wanted the correlation to be taken into account. The original original passive model-based approach computed T and R. But now I would say, anytime I'm in a state S where I think the current value of this state is 10 units, I do an action and I get to a state that is 10,000 units current value. Then you tell yourself, I shouldn't be that depressed. I'm close to a rich guy. There is this 10,000 unit state right next to me. Apparently there is an action I can do, and once in a while it will take me there. Right? So I should say, I should be closer to my neighbor. This is the real estate values. The reason people kind of, if you are not mowing your lawn, everybody else is mad at you because they feel as if, because they are stuck with you as the neighbor, their neighborhood values are going down. Okay, so in this particular case, this state finds this other state, it experienced it, it found it actually has a much better value, so it then tries to nudge its own value closer towards its neighbor's value. Do you understand this? Okay, so if you thought the state you are in is 10 units good, and then you did an action, and you experienced this other state, where the value of that particular state happens to be 10,000 units. Right? That basically means 10 is too low an estimate for the current state's value. So you need to make it closer to the next neighbor. How much closer? That depends on your learning rate. You can say, if your learning rate is very high, you might just say, I will just directly use my neighbor's value as my value. If the neighbor is rich, I must be rich too. So if that is 10,000, I am also 10,000. But the problem is, if you do the same action, next time you may not get this neighbor, you will get somebody else. It could very well be this particular action has a very, very low probability event. So for example, you do this stupid action of buying the lottery ticket, which I say stupid because nobody who understands math does lotteries. Okay? So you bought the lottery ticket, and then you bought the lottery ticket and you won. And so CNN had your face plastered. So now you can't just say, since I won once, then that means that the previous state before I bought the lottery ticket is just as good as the state after I buy the lottery. Why? Because when you buy the lottery ticket, the possibility that you will go into a state where you become rich is 1/1 trillion or something. You cannot basically, if you learn from this that you should be buying lottery tickets, you can use your $1 billion and keep on buying lottery tickets and you will have your money. That would be a pretty inoptimal plan. So what you do need to do is, there is at least one action that takes me to this better state. So let me nudge my state's value a little bit closer to my neighbor's value. Next time around some other neighbor comes, I try to become closer to their value. And if it's only a certain set of neighbors that comes to me, with certain set of predefined probabilities, then the math will work out and you will actually have nudged your value to be the expected backup value for doing this action. Did people understand what I just said? You are using the world itself to do the backup value of doing an action. Okay, so in particular, when I do this action S in A, I could have gone here, gone here. In this particular case, I went here. So what I do is I take whatever my value here and I take this guy's value to nudge closer to S dash's value. Next time around I do the same action, I might get this, in which case I do the same again, nudging. if I do this nudging, if these are the only three possibilities and I keep doing this infinitely often, the backed up value for S would be essentially the right expectation of the values it will back up from each of them. If in fact the state, you will always keep coming in this exact transition, there is no other transitions, you will still get the correct value in the end. And so the question of course is how much do you push the value towards. So what I'm going to do is I am trying to compute the value of a state S with respect to the policy part. That's what I'm trying to compute. And that's of course this one. Okay? Now, when I actually wound up doing the state action A in this state S, I experience S dash. When I experience S dash, I will right away experience RSA S dash, right? I right away experience that. Plus, I remember what I have put up until then in S dash as the value. So this is basically what I realized my neighbor is actually 10,000 good, according to my current estimate, even though I am thinking I'm only 10 good. So then what I do is I set my value to be my current value plus alpha times the sample minus current value. Okay, and this normally, this is basically your learning rate. Okay, and the smaller the learning rate, the slower the value becomes consistent with respect to your neighbor. The larger the learning rate, you're making very big jumps, and so you have to keep changing your value function more often. But if you do this, and you do this infinitely often, then you can prove that you will converge to the value function V pi. All you are doing is taking the temporal differences. Temporal difference is having the state S, I did an action, I got this state S dash, and I am essentially pushing the value of my state S to be closer to the S dash value that I experience. This is what is called temporal difference. And the beauty of this is actually there are experiments showing that brains do temporal difference. Pretty amazing stuff. And again, as I said, remember that anything brain does at the lowest level must be very simple. It's a bunch of neurons. We don't know how exactly everything works, but the individual operations have to be very simple. And in fact, there are experiments showing temporal difference learning actually occurs in mammals. Okay. Now, if you thought that the passive model-based learning was boring because it seemed like you took a couple of ratios to compute the t and then just reduce it to some problem that somebody has solved already in the past two classes because solving MVP. If you're bored thinking how small this algorithm is, you should be even more bored with this algorithm. This one doesn't even take any ratios. You're just subtracting the value you experienced from the value you currently have, and you're nudging yourself towards that value. That's it. You see what I'm saying? Amazing idea. It looks as if, why did I come, go through computer science and probability theory and all this stuff to get to ideas like this, which seem to be extremely simple. But you have to understand why they work. Why they're working is because when you keep doing this SAS dash transition, it will eventually behave as if the god of T star is guiding those transitions. The real T star is guiding those transitions, even though you don't know what the T star is. You're letting the world tell you. Of course, by the way, letting the world tell you typically should send shivers up your spine because sometimes the world will tell you that you're dead now, at which point you're dead. But this is a problem. For entire reinforcement learning, this is a problem. You actually act in the world and you might die. Okay. Of course, we can actually write scenarios where essentially we will wind up restarting the game. But when you actually die, you don't again restart the game. So there is that problem. But modulo that, this will work. I want you to actually, if you understood this, or if you're still slightly worried about where is this magic here, I'll give you a slightly different way of understanding what's going on here. Imagine you're trying to compute the mean and average of a bunch of numbers, n plus 1 numbers. They're just coming one at a time to you. So you're keeping the running average. Okay, so there's two different ways, right? One is if you have n plus 1 numbers, x0, x1, etc., all up to x1, x2, etc., all the way up to xn plus 1. Okay, you want to compute the average, you just sum the xi's divided by n plus 1. You would agree with that, right? Now, of course, you can write this as this, which is the moving average up until that point. So, in fact, one way of keeping track of averages is you keep the moving average up until the n points that you have seen, and then when the nth guy comes, you somehow have to take nth guy's effect on the overall average. Okay, so you could do that essentially by taking, so this expression can be written in this as a sum of these two expressions. Okay, and notice what I did here, I took xn plus 1, which is the new sample, subtracted it from my current moving average, which is sort of the value. I then divided it by n plus 1, which is the 1 by n plus 1 basically is the alpha now. So x hat n plus 1 is being written as xn plus 1 by n plus 1 plus the difference between the sample and the current moving average. If you look at this, it's the same. Okay? So here are some examples. You can basically, again, one of the issues that people get confused is, but show me an example. There is not much to show here. Essentially, I will take two numbers, take their difference, multiply it by alpha, add it up to the first number. That's what is temporal difference. And you just keep doing it often enough, then you magically go to the true value of each of the states. Okay, so understanding why it works is more important than how to do it on paper. But however, here's an example. So if I have alpha is half and gamma is 1, that means I'm not doing any discount. Okay, so then if I'm so in the beginning I start with a value function 0, 0, 0, 8. Okay, then I observed the following transition. I went from B east, I went to C, and I got a -2 reward. Okay, if I got a -2 reward plus the value which is 0. Okay, so the backed up value is -2. Okay, and so I need to, and then the next time, okay, and then, so at this point I'm in, of course, here, and then I have to update my current value. Okay, and what will happen to my current value? My current value will go down from 0 to -1 because the difference is -2 minus 0, which is -2, and I have to multiply it by alpha, which is half, which is -1, and then I add it to the original value, which is 0, which is 0. That is why it became -1. You feel better that you have done an example that okay. You do this many, many times, then essentially that's what temporal difference is. Okay? Actually, there's one more example. Let's see what happens. So then from here, apparently, I did C. From C, I again went to the east, and then I ended up in D. D is minus, and I got a reward -2. But however, this time -2 plus 8. So the actual reward, total value of the sample is 6. Minus 0. 6 minus 0 is 6. Divided by 2, which is the alpha. So I should be essentially setting this guy's value to 3. How many of you are wondering at this point? Why did I stop here? This guy got a new value, should this guy get a new value? You understand what I just said? Turns out there is an algorithm for that. Any simple improvements you can think of this, somebody has already come up with it. Okay? It turns out that actually if you do an entire trace, you can use the entire trace to update everybody's values every time you experience a new state. The simplest TD will only update the current state's value. But you kind of can see that, originally I thought this guy was 0, that's why I became -1, but then a little later this guy became 3, so I should be -1. Right? And I basically will do it in this simple algorithm. The next time around I wind up coming to this state and do the same action. I can improve the speed by essentially doing it right now itself. You see what I'm saying? It turns out there's some name for this. I think these are called eligibility traces, and this is, But if you understand this temporal difference learning idea, and in particular, get out of this deep feeling of disappointment, that is this what we are paying tuition for? To subtract numbers and multiply by alpha. Is this what our brain is doing? If you can get out of the disappointment, understand the beauty of this algorithm, then you are in good shape. Okay? The next thing is we have temporal difference. Now, whatever I said here, notice that, remember I said, even irrespective of, so if I want to go from here towards, so what I do here is I'm basically, when I'm doing this, if I'm following a particular policy all the time, I'm slowly going towards V pi. I'll converge to V. But I can converge towards V star by essentially doing random policy to begin with. It turns out that actually active temporal difference learning works fine. It will get you to V star. I'll tell you a little more extensions that need to be made, but pretty much the same idea. Active temporal difference learning works and you get V star. Just by doing the same differences and multiplying by actions. Now here's the question. If I give you V star, you figured out V star somehow. Now what is your policy? How do you get your policy given the V star? How do you normally get your policy given V star? Which class are you in? How do you normally get your policy given V star? In any given state, you consider each of the actions, do those actions, and consider the expected backup for each of the actions and take the action which is maximum. Do that. How to? You have V star, figure out what action to do. Why won't this work? Why won't this work? To figure out, to go from, so if I have, if I have some state and I want to figure out from this state that I should do, let's say, this action going this way or going this way. So I want to figure out which of these actions. I have to simulate both these actions in terms of if I do this action, I'll go into this state or this state or this state with these probabilities. And these are the values I'll get in those states. I take the expectation of that. And then I take the expectation for the second action to take the max. That's the action I do. Do you understand this? Do you remember this? I hope you do. Right. Why can't we do this now?
Because the probability of action is not there in this case.
That is what T is. To actually simulate the action in your mind, you need T. The whole point of passive learning is we didn't have to do T. So it's like I got finally very good food, but I have no hands to eat it with. So I see, wow, extremely good food, but how do I get there? Because the T is missing. I mean, you should feel disappointed about this, right? And if only I have T, I can change everything. But then, look, if you're doing T now, then you're not passive anymore, you're doing active. Whatever the reason you decided not to learn T should remain the same, whether you're doing active model free or passive model free. So the question now is there a way in which I can get the policy without actually having the transition function? Something close to V star I should have, but I should not have to use the transition function. Okay? That is where the Q comes. So instead of keeping track of V star of S, you keep track of Q of S A. For every state S, let's say there are 10 actions in each state. Previously, you used to have one value function for that state, V of S. Now, instead, you will have Q of SA1, Q of SA2, Q of SA3, Q of SA4, all the way up to Q of SA10. So, instead of one value function, it is 10 times that much storage, if there are 10 actions per state. If you did this, and if you actually, instead of updating the V function, you kept updating the Q function, your problem is solved. Why? Because when you're done, you know Q star of S for each of the actions. Q star of SA1, Q star of SA2, Q star of SA3, etc. Now what is the V star of S? Whichever is the best Q star. And that's just taking the max of the Q values. You didn't have to use T anymore. Did you understand what I just said? It's a pretty cute idea. And again, if you don't understand why you should be disappointed from going from V to pi, from infinity to go from V to pi, you will never understand why Q is important. No, normally you would have just done V. Instead of V, if you keep track of Q, then you don't need the transition function at all. So at every state, you know which action to do because that is the action that has the highest Q value. And each state has like 10 numbers if there are 10 actions that can be done in that state. So this is what is called Q learning. So the previous stuff is V learning. Okay, V learning is just learning. By the way, there is this name called retronym. I don't know any of you know in my continuous quest to give you here your vocabulary. Retronym is going back and changing something that you already knew because something else new came along. So for example, ovens are now called conventional ovens. Originally they were called ovens, but then there are microwave ovens. Because they're microwave ovens, you have to go back and call the conventional oven something else than just ovens. So similarly, instead of previously learning meant